direct. Ok, normalement, c'est du direct là. Évidemment, du coup, il doit y avoir probablement un lag, mais on va attendre direct. Je crois qu'il y a un lag de 5 minutes.
Ouais. La vision.
Ouais, super. Ok, j'ai plus rien à faire de ce côté-là, a priori.
Okay. Donc la...
Tatiana est toujours pas connectée. Mais...
Ouais. On regarde ce qu'il voit, Thomas. On bouge la...
Ah, mais attends, mais si Thomas, regarde là, il voit plein de trucs, là, il voit un truc à 360.
Oui, en haut.
Ah, ouais. Mais ça bouge pas le reste. Ouais. Allô, test.
Tu vois que moi, Thomas, là, hein?
Ouais, pour l'instant, ouais.
Ok. Et puis en plus, regarde, comme ça, il ne verra pas super bien.
Ouais.
Si.
Je trouve que la caméra est plus... Si on a que ça...
Oui, en haut.
Mais ça bouge pas le reste.
Ah, on va couper la sortie quand tu... Que moi,
je coupe. Il y a un lag.
C'est normal, c'est YouTube, je pense.
Non, j'ai coupé YouTube. J'ai plus YouTube.
La diffusion...
J'ai plus YouTube. Attends, Firefox. Je vais faire Firefox. Je vais couper. Non, j'ai plus YouTube. J'ai coupé mon YouTube.
On va couper la sortie quand tu vas parler. Pour pas que ça revienne dans le micro.
Coupe la sortie de
ça.
Ok, mais du coup, ça sortira de là.
Non, après tu la remets.
Ah oui, ok, d'accord, bien sûr.
Ouais,
oui, bah,
parce que tu vas parler tout seul.
Je fais ça, quoi.
Thomas, il va pas faire chier pendant que tu parles.
Je fais ça. On est d'accord?
Ouais.
Ok, ça marche.
Donc ça, c'est bon. Par contre, ce qu'il va vouloir, les gens... Ah, ça y est.
Hello, Tatiana? Can you hear us? C'est live là sur YouTube. Hello, Tatiana?
Hi.
Can you hear us?
Yes.
Great. Welcome to Paris in remote.
Thank you.
Ouais, je pense. Je vais mettre le PowerPoint en visualisé là. Normally, both of you, Tatiana and Thomas, you should be able to see my screen,
yes.
Right?
Yes,
Perfect.
yes, I can see it.
Thank you. J'ai plus de notifications. Je me dis un peu tout le monde. Mais...
Oh, moi j'aime bien.
Voilà.
Ok.
Elle peut nous entendre.
Hein?
Elle peut nous entendre.
Ouais. Hello.
Salut.
Salut. Salut Thomas. Hi Tatiana.
Hi.
Est-ce qu'ils vont aussi là?
Ouais.
Ça là, c'était quand même.
Alors,
Eux,
non.
à distance, machin. Non, mais ils n'ont pas fait normalement.
Tu veux que je le mette?
Oui, ils n'ont pas fait.
Non.
Ah.
Ok. Ah, descends. Ok. Normalement, c'est live sur YouTube. J'avoue ça.
Ouais. Ok, il faudrait. C'est parti le live.
Il est parti là, il est parti. Ouais.
Ok.
Je suspendrai, t'inquiète. On verra ça, ouais.
So if it's okay, we can start. So today in the committee we have Jan Narlis from Navier Labs, David Fia from Insta and they are the leaders. And we have also Tatiana Tomasi from Politecnico di Torino, Kartik Alari from INRIA Grenoble, Mathieu Corp, who was a supervisor, Thomas Robert from Euritech, and myself, Kevin Bell. So you have 45 minutes to present your work.
Thank you, and welcome to my presentation of my PhD defense talk, Continual Learning for Computer Vision, Learning Continuously Without Forgetting. So first of all, I'm a CIF PhD, meaning I'm working in a company. So I'm going to explain what is this company doing. What we do, we analyze images on the web, such as Instagram and Weibo, which are unstructured data, images, and we, through multiple models, transform them to structured data. Meaning, for example, I can say that in this image, there is a woman that is wearing a bag, luggage by Celine. There is a trapeze, zip, pocket, and leather attributes, and also colors, such as beige or black, for example. One thing that is interesting is we have multiple classifiers. Here, for example, classifier for the bag, in order to know which kind of bag is it. But the question is, what if we need to add a new kind of bags to classify? So first of all, in computer vision, we're going to work in deep neural networks. It's going to be a function that is going to take input an image, and then through this function, produce an array of probabilities, one probability for each class. Here, 95% for the cat probability, and 5% for the dog probability. How does a deep neural network work in practice? It's usually based on convolution. So here you can see convolution in yellow, pooling yellow in green, in red, and classifier in blue. The forward pass will do a transformation of the image to multiple convolution, pooling, and then the classifier to produce the probability. In order to learn those parameters, we're going to compute a loss function. This function will tell our model how well or how bad it was able to classify it, and how it should change its prediction based on the gradient descent by computing the gradient of the loss with respect to each parameter of the model. What is very interesting in this kind of models, convolutional neural networks, is they are going to learn different kinds of information, of patterns through the network. At first, the first few convolutions will learn very basic patterns, such as, for example, edges or textures. Then all those patterns will be combined together in order to build a more complex understanding of the image, until learning patterns, parts, and even objects, making the task for the classifier to discriminate between classes much easier. Right now, most of the models in the deep learning community are trained in independent and identically distributed training, meaning we have a model, F0, which is initialized randomly, and then we're going to train it on 10 new classes. Here, classes from 1 to 10. It will produce a new model, F1, that will be then evaluated on the same set of classes, classes from 1 to 10. But the question is, what if we want to reuse existing knowledge in order to learn a new task? And that will be transfer learning. Well, in transfer learning, there is an upstream task and a downstream task. In the upstream task, we're going, as before, to learn the classes from 1 to 10. Then we're going to use this knowledge based on the model F1 to learn new classes, classes from 11 to 20, and produce a new model, F2. That is there, will be evaluated on the new set of classes, classes from 11 to 20. But the problem is, what if we wanted to learn these new classes, but also keep the remaining knowledge, classes from 1 to 10? And that will be continual learning, where the model, F2, has only evaluated on the new classes, classes from 11 to 20, but then we want to train on the new classes, but then we want to evaluate it on all classes, classes from 1 to 20. The problem is we cannot always use the previous data for multiple reasons, such as, for example, privacy. For legal reasons, for example, if I'm working on medical data, sometimes I can train a model on medical data, then I have to discard this data. Also storage, for example, because I cannot have unlimited storage to store all the data. And even the most important one, time. Because if we need to retrain on all previous data, it's going to take a lot of time. Content learning, evidently, doesn't stop at 2 tasks, but it can do 3 tasks, 4 tasks. There is truly no limit until the model starts to collapse. What is interesting and to understand what is the challenge of content learning is to look how the optimization behaves in content learning. Here, on a very basic, simple example, I'm going to optimize the loss with SGD. So you can see the optimization process with the arrow that go to the local optimum in blue of the first task. Then I'm going to learn the second task with different classes, different data. So we're going to reuse the previous knowledge. So we start not randomly, but we start from the previous optimum in blue, and we go to the new optimum in red, as you can see here. But the problem is, what if we compare this content learning, task 1 and then task 2, to a joint training, where we'll have access to both the first task and the second task all together. And you can see the optimization problem is over there, and the optimum, when having access to all tasks, is very different from both the first optimum in blue and the new optimum in red. Meaning that this discrepancy and will be the performance of both blue and red will be suboptimal, instead as if we have trained individually for each of them. Let's take another example with Cypher 100. Cypher 100 is a data set of images, small images of 100 classes. We're going to learn here a model, a deep convolutional neural network on these models, learn classes per classes. Here, 10 classes, then 10 more classes, and etc. until we have learned all classes. In blue, I'm plotting a very Oracle model that is very basic, that is only retraining on all seen classes. On the first step, I'm learning classes from 1 to 10. Then on the second step, I'm learning classes from 1 to 20, and etc. Meaning every time I have to access to all previous data, and I'm evaluating my model on all seen classes. Obviously, there is a decrease of performance. We went to 85% of accuracy to 75, but it's normal because we went to classifying only 10 classes to 100 classes, a much more harder fit. But if we look at the continual model in orange, where here it will be only fine-tuned on the new data. Meaning at the first step, I'm learning the 10 first classes. Then on the second step, I'm learning only on the 10 following classes without having access to the previous data. And we can see that very quickly, the performance drop off. And at the end, the forgetting is so big, we call it a catastrophic forgetting. Because we go to the optimum of the new task and very far to the old optimum of the old task. Meaning we're going to forget all previous classes. Therefore, that's so bad that the final accuracy is only 5%, 9%. So actually, the model is not usable at all. Using the final accuracy is interesting, but we also want to record all different accuracies. Because in a true control learning model, there won't be a final task. Each task could be a final task, or then it could be improved. Therefore, we need to focus on every task, meaning that the average of each step is also an important metric to understand if our model performs well or not. During this PhD thesis, we had multiple motivations. First, a motivation that is having a stable representation in order to not to forget, to have the same representation from both the first and second task, but also to have a dynamic architecture, because as more tasks are coming, our model maybe risk to be under-parameterized, and we need to expand the number of parameters to tackle this growing complexity. This motivation will decline across multiple axes: constraint, rehearsal, and conditioning, each made on different contribution, first pod, then second object rehearsal, and finally in the third part, datox. First of all, I'm going to talk about pod, based on constraint, based on visual features constraint. This chapter has led to 2 publications, one at ECCB 2020 and one at CVPR 2021. Our setting, we're going to base ourselves in image classification, class incremental, meaning we're going to learn classes, a set of classes, here, for example, the 10 first classes, then the 10 following classes, and etc. Every time evaluating on all seen classes. Evidently, it's quite hard to tackle big data sets, such as ImageNet. Therefore, we're going to allow ourselves to review a previous amount, but limited amount, of the previous classes in the memory, or the rehearsal memory. On the second task, I'm learning classes from 11 to 20, around maybe 500 classes for each new class, 500 images for each new class. But in the memory, I'm allowing myself to store maybe 20 images per class. Rehearsal learning is actually not enough. So simply using rehearsal learning won't solve catastrophic forgetting. I'm showing you the same example as before, learning 10 classes and 10 classes, which is quite an easy setting in control learning. And despite the fact that the rehearsal learning here in green has better performance than the naive model, because it allows itself to see previous data, but still is very far from being close to the optimum in blue. So what can we do in addition to the rehearsal learning in order to reduce this forgetting? We can do distillation on probabilities. Constraint aim that the new model will have a similar behavior as the old model on the same images. Meaning, if the old model had predicted some probabilities for an images of an old class, we want the new model to predict the same exact probability in order not to forget. So what we do on the constraint probabilities, we're going to focus here on the top model is the new model. On the bottom is the old model, ft and ft-1. And we're going to force that the probability of the new model, pt, to be similar to pt-1, the old probabilities. So evidently, we only take into account the probabilities of the class in common between two models, and we're going to minimize either the Cayley divergence or cross-entropy between both. This is very inspired from the literature of model compression with Dolph Winton. Then, later model proposed that instead of focusing only on the probabilities, we could also focus on the final embedding, here, ht and ht-1. This final embedding is the flat embedding after the global average pooling gap in green. So what they do, they force that they maximize the cosine similarity between the two embeddings. in order to reduce the forgetting. And this loss can be used complementary with also focusing on the probabilities. But we wonder, no one tried to constrain the whole network, and maybe could that be a good axis? Because we want that the new model to be similar to the old model. Therefore, maybe simply constraining the output, probabilities of final embedding, is not enough, and maybe we should constrain the whole network. So we tried. We took features, visual features. So as you can see here, there is a channel, width, and height axis for each different block of our ResNet, and we try to minimize L2 distance between the visual features of the new model on the right and the old model on the left. But actually, it doesn't work. So it was quite a disappointment for us. You can see here the performance of not using a loss, 53, and the performance of using this loss, 49. So it's lower, actually, because we tuned the hyperparameter in order to forget less the first classes. But the fact that our model was able to forget way less the old classes, but still it was also too rigid, meaning that because it was mimicking perfectly the features of the old model, it wasn't able to change to be plastic enough in order to learn the new classes, which evidently is a problem because in content learning, we don't want to forget, but we also want to learn new classes. So the problem is that this loss was way too rigid and couldn't learn new classes. And moreover, there was no invariance in these losses, meaning that we tried to mimic perfectly the old model, which kind of makes sense in the literature of compression, where there is a very big teacher model that is quite perfect compared to a small imperfect model. But here in this case, the old model, ft-1, is a model that also went through continual learning process and maybe also at forgetting itself, meaning that it's imperfect model. And it leads us to the rigidity versus plasticity trade-off. So we have a loss, classif, that we begin to learn new classes, which is the plasticity, in order to be plastic enough to learn new classes. But we also have the distillation loss, which is a rigidity, in order to be rigid, in order to not to change too much, to not forget. And we need to balance efficiently those two losses. But the previous losses I've shown you was way too rigid and not plastic enough. So our intuition was, can we get some invariance compared to the previous model? Invariance in computer vision relative to transformation in the image can be achieved with pooling. So maybe we could do the same pooling in order to give slack, some kind of degree of freedom to the model in order to mimic the old model, to be rigid, but not too much in order to be plastic enough. So empirically, we tried multiple poolings. For example, the channel pooling, where we pool the channel axis, but also the global area pooling, the width pooling, and the height pooling. And you can see all these different pooling, which are quite different, but all improve significantly the performance of our model, from 53 to 57 and even 60. So we found that using this kind of pooling, so all pooling were efficient in order to give rigidity versus plasticity trade-off. And furthermore, we found empirically that the best pooling, pose spatial, which was a combination of both the pose width and the pose height, give us the best performance with a C times W plus H constraints. We evaluate our model on two datasets, CIFAR, which are small images made of 100 classes, and also the very challenging ImageNet, large images made of 1 million images of 1,000 classes. So we evaluate first on CIFAR. You can see here the performance of UC and BIC, where the previous state of the art, and iCarl, quite a similar model in this literature. You can see that our performance here, we're going first to learn 50 classes, so half of the classes. Then we're going to learn the remaining classes here in 5 steps, because each step is made of 10 classes. Performance of that is quite equivalent to UC and above the other. But what's interesting is as soon as we reduce the amount of new classes per task, meaning evidently we need to increase the number of tasks to learn. And in this situation, the drift, the catastrophic forgetting, is even more exemplified as there is more steps, therefore more possibility to have a catastrophic forgetting. And on the other hand, also, there is less new classes for each steps, so it's very easy to overfit on these few new classes and therefore forget also. And you can see that as soon as you reduce the amount of new classes per step and therefore increase the number of steps until the very challenging 50 steps of one class each, we can see the performance of all models decreased significantly. You see went from 63, 60, 56, and 48, while our model still has forgotten, but went from 64, 64, 62, and 61. A very slight decrease of performance compared to the other model, which can be more seen on this plot while I'm comparing PodNet in red to the other models. PodNet suffer from forgetting, but as we say, the graceful forgetting, while the other models, you can see that as soon as the first 5 new classes, the first 5 steps, they forget significantly and went from 80% accuracy to to 50% of accuracy, which is significantly a catastrophic forgetting. We also evaluated on ImageNet. As you can see here on ImageNet, we evaluated both on the ImageNet niche datasets, where we learn still half of the classes and then the remaining classes in continuous steps. And we also evaluated on the smaller subset of ImageNet 100, made of 100 classes, which allow ourselves to try different settings. And you can see that on each CodeNet, our model outperforms significantly the state-of-the-art in every setting. Now, a final experiment that is also interesting is, as I said before, the loss is made of the loss of the classification and the loss of the distillation. Usually, the loss of the classification doesn't add any hyperparameter, but we have an hyperparameter here, lambda, for the loss of the distillation. The higher the lambda it is, the more constraintful our loss it is, and therefore it should forget less, but also it should forget so much less that it won't be able to learn new classes. It won't be plastic enough. So we evaluated here on this table a setting where we change the number of images that we store per whole class in the rehearsal learning memory. In our experiment, we only store 20 images. But what if we store only 5 images per class, or the opposite, 200 images? If we store 200 images, it means we have access to a lot of the previous data, and therefore we won't forget that much, and we maybe want to learn quite efficiently on this whole data and be plastic enough. Therefore, our lambda should be small. On the other hand, if we have very small amount of images per whole class, we risk to forget a lot. And in this situation, the loss of the distillation has a lot of importance. Therefore, this lambda must be big. And we can see that our model, using the same lambda, a fixed lambda, tuned once, in every setting, outperform all state-of-the-art. So big, which was a very plastic model, so very efficient on the setting of plastic setting with a lot of images, is equivalent to our model. But as soon as we go in the other model, other situation, in 5 images per class, where we need to be rigid, our model could still outperform the other models, meaning it was able to trade off efficiently between the plasticity and the rigidity while using the same lambda in every settings. So previously, only explained about image classification, where we have only one label per image. So as you can see here, I have a label for the core, a label for the car. But what if we go to another setting, semantic segmentation? In this case, we have multiple classes, multiple labels per image, where each pixel has a label. You can see here, co is labeled in green. The black pixel are actually background, which is kind of an empty class for everything else. And we also have on the bottom the class person in red and the class table in yellow. In this situation, we tried, we still have the same problem of forgetting, so we tried, maybe as pod was working very well, we could apply it in this situation. So we added here the mean intersection over union, also called the Jakarta Index. It's a metric between 0 and 100, and we want to maximize it. We tried the knowledge distillation that I shown you previously, where we constraint the probabilities, and also evaluated the UNKD, which is a knowledge distillation made explicitly for continual segmentation. So it was supposed to have better performance, and it did. And we evaluated pod, our loss. And you can see that pod outperformed in almost all metrics the other losses quite significantly. But still, it was not enough, as we wondered, semantic segmentation is actually very different from classification. In classification, there is only one label per image, which is not the case for segmentation. In classification, we use a global average pooling at the end of the convolutional neural networks to give it to a classifier. We cannot do it in segmentation, obviously. Therefore, doing a width pooling and height pooling across the whole axis of the features didn't make sense, as we were kind of capturing a global scale, while in segmentation, we're focused also on smaller scales. So we tried multiple alternatives, and we found that the best one by using both the multi-scale, so a big scale, for example, here on the left, a scale on the whole axis of the width and the height, but also smaller scale, here, for example, a quarter of the image. Evidently, because we do it on quarter of the image, we have 4 loss on the smaller scale and only 1 loss in the bigger scale, meaning we give more emphasis to the smaller scales than the bigger scale. But both are important. And we combine them in one single loss, local pod, that we found that outperforms significantly both pod and all the other losses. So the claim for this chapter is that constraining is important and is a good axis to reduce this continual the catastrophic forgetting, and that constraint should be applied not only at the final probabilities or the final embedding, but should be applied at every steps of the model, because we want that the whole model not to forget. This constraint, furthermore, should balance efficiently the relative pseudoplasticity. So we can balance this more or less by tuning the lambda per parameter, but it's even more efficient if we can induce directly in the definition of the loss this trade-off. And finally, for the computer vision field, the spatial locality is actually a very important factor that should be also incorporated into the distillation loss. Now, I'm still focusing on the stable augmentation motivation. We want to reduce the forgetting. Previously, we tried to have constraint in order to force the model, the new model, to be quite similar to the old model. But that can also be doing in another way by doing rehearsal learning. Rehearsal learning about reviewing previous images. If we review a sufficient amount of previous images, our new model should be quite similar. As you can see, it will be similar to a joint task training, meaning we will reduce this forgetting. So we try it with object rehearsal. This led to a publication at CPR 2021 and a submission to a paper, a journal paper at TPAMI. So controlled segmentation, it's a setting very recent, initiated by Chermeli et al. In the first step, we're going to learn the class car. So as you can see, the ground truth, the class car is in yellow, and we're going to learn it and classify it. Then we're going to learn the class person in red. But as you can see, the ground truth on the top, only the class person is labeled in red, while all of the other classes that could be in the image are not labeled anymore. For example, the class car is not labeled, but our model on the bottom has to predict both the new class in red, car person, and the old class in yellow, car. Likewise, in the first step, if I'm learning the class bicycle, only the bicycle is labeled, but at every step, all classes, scene classes must be labeled. What is challenging is that every step, for example, here on the second step, both the past class and the future class could be present in the image, but hidden, not labeled, hidden in the background. So our intention was that we don't have a rehearsal learning in this setting usually, but images can actually contain previous classes that could be hidden in the background label. So maybe we could use it, uncover it, and use it as some kind of implicit rehearsal. So we tried that. First, we're going to learn the class person, we predict the class person. On the second step, we're going to learn the class table in yellow. And we're going to use the previous model that has learned just recently the class person to pseudo-labelize all the pixels in black of the background that could maybe hide some kind of old classes. So we pseudo-labelize it, and our new ground truth is made of the real perfect ground truth of the table and the imperfect pseudo-label of the person. And we learn on this model. Likewise, for the third task, we do the same. But this time, we reuse not the first model, but the model from the second task, which has learned the class person and the class table. Obviously, the second model may have forgotten and is imperfect, and therefore we don't want to produce imperfect pseudo-label and to propagate errors through every task. Therefore, we do some kind of uncertainty base from Jakarta et al., meaning we're not going to use all pseudo-label, but only pseudo-label that are confident enough. We evaluate a model still is the mean intersection behavior union. We tried multiple losses. First, CE means cross entropy. So we try cross entropy only on the new labels. So cross entropy only on the pixel that we are sure it's a new class, not cross entropy on the background pixel, which could hide maybe a background class or not. So this doesn't work at all, actually. We also tried the cross entropy, which is barely working, and the UNCE, which is a modified cross entropy made especially for controlled segmentation and which brought a significant improvement over the cross entropy. And then we tried our pseudo-labeling loss, which outperforms significantly all models. Which is interesting is the pseudo-oracle. Pseudo-oracle is, what if my pseudo-labeling has made a mistake? Therefore, we authorize ourselves in the pseudo-oracle to fix that mistakes, meaning that pseudo-oracle is obviously not a real realistic loss, but it's kind of upper bound. And you can see that pseudo is obviously lower of the upper bound, but still very close to the upper bound, meaning that our pseudo-labeling loss is quite efficient. We combine both the pseudo-labeling loss with the local pod that I've shown you previously in the previous chapter, in one single model called PLOP. We evaluate our model on multiple data sets, including Pascal Vogue made of 20 classes. In the 19.1 setting and the 15.5 settings, for example, I'm going to learn in two tasks. 19.1 meaning I'm learning 19 classes, then 1. 15.5, I'm learning 15 classes, then 5. We see still the mean intersection behavior union, MIB, the previous state of the art at CPR 2020, is actually quite similar to PLOP in terms of performance. What is interesting is as soon as we add more tasks, meaning we're going to learn less classes per task. In the class setting of 15.1, I'm going to learn 15 classes, then 1, then 1, until I'm learning all 20 classes. You can see that other models such as EWC, LWF, and ELT start to forget dramatically, and they're actually not usable anymore. MIB forget also significantly, and our model, PLOP, managed to be in almost all metrics double the performance of the previous state-of-the-art by a significant margin. In semantic segmentation, it's always nice to also see the visualization. So in the first step, we're going to learn 15 classes, the same classes as PLOP, and you can see that our model as MIB and PLOP and MIB in the first step are equivalent. But as soon as we add more classes, here we learn the class plant, then we learn the class ship, and etc., you can see that MIB start to forget. And for example, there is no table anymore almost in front of the person, and the bird is starting to be classified either as a dog or a sheep. And at the end, the poor child is only eating in front of a train in light green, while our model still managed to retain the table knowledge, evidently with some imperfection. Likewise, the bird is actually now a sheep in brown, while our model is still in yellow as a bird. But we still have some imperfection as our model is not yet perfect, of course. In other settings, we also learn here 15 classes. We learn the class person, then we're going to learn new classes, the class car, boat, dog, etc. Then in the 5th steps, I'm going to learn the class train. Here it's interesting because the class train previously, I saw it as a background class. So it was hidden. And now I'm going to see it again, but here as a real class labeled. And you can see that MIB struggled to learn efficiently this new class train while keeping the knowledge of class person. And at the end, you can see that there is no more person that will have been eaten by the train, while we, with some imperfection, managed to balance both the class person and the class train together. So apparently, pseudo-labeling is perfect, and it's an implicit rehearsal good enough, so we can start it under the paper, but actually not. Because pseudo-labeling has a very big failure case, is that the pseudo-labeling can only uncover classes in the background when they occur in the background. And the problem is, for example, in the 5th steps, when I'm learning the class train, there's a class train here, but class train never occur with, for example, a dining table, a cow, or a chair, meaning that if they never occur together, it's not in the background, and I cannot uncover it with pseudo-labeling. Therefore, we need to do something. So we tried image rehearsal. So image rehearsal, as shown previously, I'm going to keep previous images. Evidently, these previous images are partially labeled, so at each step, I need to pseudo-labelize it. You can see that the performance of image rehearsal is much better than not using rehearsal, evidently, but still using quite a significant amount of memory, 22 megabytes. So there's several problems. First, it's partially labeled, so we have to assume that also labeling will be good enough to complete this kind of image rehearsal. Furthermore, they are very fewly informative. 63% of VOC is actually made of background, and 32% of cityscape is made of fraud. So at some point, these classes are well learned, and we need only to focus on what is informative. And furthermore, in segmentation, the images are quite usually very large, meaning they are heavy to store. So we wonder what if we can simply store and rehearse what is important. So here we're going to simply extract the objects, which are sometimes imperfect, and put it in the object rehearsal memory. You can see here the object of bus, dog, and bird. They are very informative, and we are sure of their label. And furthermore, they're obviously magnitude lighter than simply using the whole image. So we're going to first, you can see, learn on the new classes, for example, the class ship, and learn on the old classes by pasting this object into a blank image and combine all together into a single loss. And we're going to learn on this. You can see that the memory is only 2 megabytes, so almost 10 times lower, but the performance are also very bad. And it's even worse than simply not using object rehearsal, which is a problem. So we try instead to use the background because the model needs some context in order to learn the class. It cannot simply learn the pixel of the class, it needs also the context surrounding it as some kind of correlation. So we passed it, here the bird, on the new images. So the bird is passed, for example, on the grass of the ship. And we can see the performance start to increase significantly and are no better than not using rehearsal. But unfortunately, they are still lower than using the whole image rehearsal. Because of the interference between the original image objects, it's actually quite hard to define an heuristic in order to see where the bird should be passed on the image. Therefore, there is sometimes interference where the bird is badly passed on top of the ship, which can lead to bad performance. So our solution was simply do a foreground erasing, where we still do the pasting, but then we erase, replacing by black pixel the object, for example, of the ship, and we discard the pixel in the loss, and you can see that the performance here starts to increase significantly to be either above or equivalent to the image rehearsal settings, while having much less megabyte to store. So the claims for this chapter is that background shift, where only classes are partially labeled,
Yeah, I think we lost Arthur. I just sent a text to Mathieu.
Okay, thanks.
Ah, c'est Jean-Pierre qui est dedans. T'as un BPM
il n'est pas lancé le Jean-Pierre. Il n'est pas lancé le Jean-Pierre. Non, il n'est pas lancé. Okay. Can you hear us?
Ouais, c'est bon.
Yes.
Si YouTube est là, okay. Okay, it should be good. You should see my screen again. Okay, very sorry.
Yes.
Sorry for this internet. Ready? Yeah. Okay, great. So now I'm going to present you my last chapter. So first of all, we tried to have a stable representation to reduce the forgetting. So we tried both constraint and rehearsal learning. And in the second step and the third step, I'm going to focus on dynamic architecture, where we'll expand the parameters in order to learn efficiently the growing complexity of tasks. We're going to do that by conditioning. It will lead us to the model DITOX that has actually been published at CPPR 2022. In our setting, we're going back memory of 20 images per class. We first read and Ah, c'est revu? Bien résumé que j'ai là. Ok. Okay. So apparently, no, I have Ethernet 4G.
Okay.
Oh, sorry. So I'm going again for this slide. So our source of inspiration was there, which was published at the CVPR 2021. It was actually training one ResNet task. Evidently, the performances are great. Each ResNet specialized for a task. On the other hand, by training one ResNet per task, if I'm running, for example, 100 tasks, I'm going to have 100 ResNet, which is impracticable in terms of memory. So in order to reduce this, but quite imperfectly, they try to do a complex and hyperparameter-sensitive parameter pruning in order to reduce the overall parameter counts and to have a similar amount of parameters compared to the other baselines. So we thought that dynamic architecture, where they expand the number of parameters and specialize embeddings for each task, was actually very interesting and very powerful. But we had different desiderata. Our first desiderata was that we wanted to have a limited memory overhead in order not to explode simply the number of parameters. Furthermore, we want also to have a limited time overhead because our model needs to be possible to be used efficiently and not growing in complexity of time every task that is learning. And finally, we wanted to have no setting-specific hyperparameters. The same model could work efficiently without any tuning for 10 steps or 50 steps, for example. So we base ourselves on the visual transformer. Transformers are based on multiple patches and then giving to a transformer encoder made of multiple blocks. We process to a self-intention as the others, and that we gather class information that will be useful and then given to the MLP head in order to be classified as classes. So based on this, we take our image and we split it into multiple patches. Then we give it to a unique transformer encoder made of multiple, here, 5 self-attention blocks. It's very important here because we have a shared computation. All the tasks will share the same kind of encoder, meaning that there is less overhead, but also there is a sharing of knowledge between all tasks together. Then we're going to decode each file. So this is the patch token, which are task agnostic embedding. We're going to decode it through the dynamic task decoder. It will be given to a TIB, a task attention block in blue, with also alongside a task token here, theta1. It will produce E1, which will be a task-specific embedding for the first task. And then classifier, it will produce the class logits of the first task. This TAB is actually a modification of the self-attention. So the self-attention is usually of the attention. But here it's different because our query, Q in red, only depends of the task token and not of the task token and the patch token anymore. Meaning that now the self-attention in yellow has a linear complexity. Meaning it's okay. So again, now it's my 4G. I hope it won't break anymore. It's unfortunate. Okay. 35 minutes. So I'm going to share the parameter among all both TAB, and meaning that simply the TAB will be the same, but will be conditioned by a different task token. Likewise, if I want to learn 3 tasks or even more, simply I need to spin up new task token. So during the training, it's made of 2 phases: the main training phase and the incremental fine-tuning phase. So in the first steps, we're going to freeze all task token, theta 1 and theta 2, for example, and all classifier also, and fine-tune all the other new parameters of the dynamic task decoder and the encoder. Then, in the fine-tuning phase, I'm going to balance the data to have as much new data as old data, and we're going to freeze the whole encoder. It's very useful in order to calibrate the classifiers. The overhead in terms of memory is very small because we only add a new task token per task. Task token is very small, it's only a 0.004% of overhead in terms of parameters. Furthermore, the computational overhead is quite small because it's only one more linear attention forward to the TAB per task. So only a 2% overhead, which can be limited to 1% if we use a single tab forward using a mask attention to do the forward with all task tokens together. So we do the ablation on a Cypher 100 with 50 steps. So we tried at first the basic transformer, which is actually not very good for content learning, meaning using a transformer by itself won't solve the problem. Then we add knowledge distillation and fine-tuning in order to improve the performance. But as soon as we add the task expansion, where we have not a single task token as a class token for all classes, but one per task, you can see the performance start to increase significantly. Then we add a divergence classifier, which is very useful in order to discriminate and increase diversity among the task token. And finally, there was using all task-specific embedding into one single unified classifier. In our case, each task-specific embedding is given to a task-specific classifier, leading to increased performance. We evaluate our model on multiple datasets, including the challenging ImageNet 1000, and you can see that our performance on both top 1 and top 5, we outperform the state-of-the-art there by a significant margin, which itself outperforms the state-of-the-art by a significant margin. We evaluate our model here on the plot. As you can see, that the performance of Datox are above the others. What is interesting is that simply using transformer for ImageNet was not giving better performance because it was transformer which is known to be good on large-scale datasets. As you can see on the first steps, where I'm going to learn, for example, 100 classes, you can see the performance here, not in continual fashion, are actually quite similar or even lower than the other models. But our model and our framework is able to forget less than the other frameworks. Finally, also on the Cypher 100 datasets, what is interesting, we learn the model in different steps. For example, learning the 100 classes in 10 steps, 20 steps, or even 50 steps. You can see here on the first plot that the performance of accuracy in each different steps between there and us are actually quite equivalent, with there being slightly above us. But what is interesting is on the plot on the bottom. As you can see here, we plot the number of parameters, and our model increased the number of parameters from 1073 to 1074 to 1077, which is a slight improvement, while our there, for example, go to 100 parameters, 100 million parameters, to 200 million parameters, to 500 million parameters. So much more bigger amount of parameters, while not a significant gain of accuracy compared to us. So our claim for this chapter was that parameter expansion is actually a very powerful way to learn continual learning, but they should, by itself, limit the time and memory overhead if you want models that can be useful, used by everyone. Furthermore, to do that, we should share common features by sharing a common encoder. First of all, we reduce the overhead in both memory and time, and we are able to share information among all tasks, which could provide maybe backward and forward transfer. Finally, task conditioning is an important way in order to do this this parameter expansion, and we found that self-attention is actually a very efficient task conditioning to enable complex feature modulation. So in this thesis, I focused on 2 motivations, having a stable computation and having a dynamic architecture, both of them aiming to reduce the forgetting to learn efficiently in continual fashion. We have multiple axes, constraint, rehearsal, and conditioning, each made of different models. Code, where we constraint the visual features, object rehearsal with a more efficient rehearsal learning, and Datox with a dynamic expansion with conditioning. There is many perspectives of content learning, as I think it's one of the fields that will be the most important for the future of artificial intelligence. One thing that is problematic is right now we focus on using very little amount of the old data. only, for example, 20 images per class. But does that really matter? Because right now, the privacy case is actually quite rare, and the disk storage issue is not an issue, because storage is very cheap. So memory maybe is not the issue, but maybe time is the essence. As maybe we want to have a more total model that should be able to learn quickly new classes, because it has learned many different tasks, and therefore it should be able to reuse efficiently this knowledge to learn more efficiently and more quickly new classes without taking a lot of time, while taking less time and retraining from scratch. Another problem is that we often say that we want to reduce the forgetting. We want actually to eliminate the forgetting. But do we really want to forget never? Because at some point, sometime, the forgetting could be beneficial as in humans. Maybe we want to forget something because it's not useful anymore. Maybe because forgetting this small information could be more useful in order to learn new information. So maybe some kind of careful forgetting should be done. And we could also allow ourselves to forget, but on the other hand, force our model to be able to relearn this forgotten knowledge quicker than previously, using some kind of meta-learning fashion. Finally, we think that simply using pre-training on the first 10 classes is actually not realistic and not efficient for control learning. Control learning could be greatly improved by using a better pre-training. This pre-training should include multiple stuffs, including, for example, self-supervised, in order to learn more task-agnostic features that could be more easily transferable to new tasks, but also new asset pre-training that could have bigger data sets, more diverse, and possibly using different modalities in order to be able to close the gap between all modalities to learn new tasks together. And finally, maybe more far shoot, is also, I think, a notion that could be important for the future is the composition of experts. One thing that could be useful as in human in order to learn, we are basing ourselves on a composition of could knowledge and could composition this knowledge together into more complex knowledge. We should be able, to have a true learning model, to have some kind of composition of expert that could be learned for first on a very basic task, and this task should be combined together in order to learn more efficiently new tasks. And one possible axis for this, which has led to a few papers actually in the literature, is based on mixture of experts, for example, where learning new experts should be based on the knowledge of all experts. So during this PhD thesis, I was very lucky to contribute with multiple co-authors, that many of them are present here, to control learning. I made multiple contributions as first author, but also as a co-author at multiple papers and journal. And I have now finished my presentation, and I welcome your question.
Thank you very much for your presentation. We can start the question with the analyst.
Can you just check that they are...
Can you hear us?
Yep.
Question.
Yes.
Tell us if you cannot hear us. Diane is starting to talk.
So, first of all, I would like to thank you for the invitation to be part of the jury. I really enjoyed reading the manuscript. I think it's very well written, and well, it presents quite a few contributions to the continual field. So, and I think the result is a very consistent piece of work, and all the chapters are very well connected. And I think this also reflects in the presentation we showed today. That was very clear and well illustrated. So thank you very much. I think that was a very good overview of the work. And I have quite a few questions for you, but I'll select a few of them. So if that's okay, we'll go through the different chapters eventually. And I'd like to start with chapter 3 that presents the first contributions of the PhD. And there you propose a method that exploits the intermediate features to reduce the forgetting, right? The probability.
Yes.
So if you want to go to a slide directly, that would be slide 37, actually. And there, you need to perform spatial-based distillation. And it's composed of two, right? The flat one for the final feature and the spatial one for the intermediate feature. And you have this very interesting ablation study that shows that there's a right trade-off that you need to find between the plasticity and the rigidity to have the best results. And you showed your ablation here on, if I remember correctly,
yes.
And I was wondering if you have an intuition how these results are specific to this set of 100 classes, or if you foresee that some of this regularization would be, well, different kind of distillation would better suit different types of classes. For example, if you have more rigid class or more flexible classes, or certain domains, or if there's some of these conclusions that would change a bit if you explore different domains, different classes. And even if, and I guess this is also related to the next chapter, but if some of this conclusion could change if you look at something different in class.
Yeah, definitely. That's a good question. I can answer in two ways. First, so yes, these losses has some intuition about what kind of classes we're going to learn. POD, as you may have seen in the manuscript, work very well when the first pre-training task has a lot of classes. It works if there is very few classes, because it needs to have actually good pre-training in order to have a good estimation of what the features are. And as it's very feature-based, it's worked very well if it's the big first task is quite big. If the first task is smaller, you can see there is actually an experiment, and I think an appendix, where we show that PodNet is slightly above or equivalent to the other model if the first task is too small. So there is one part. We need a better pre-training. And also, as you can say and see, POD is actually based on feature and is completely class agnostic. So it's definitely it's applicable to a lot of different settings, but it's probably not the best one, as maybe we could imagine, if we have some kind of information about the classes, we could maybe imagine some kind of hierarchical distillation loss that could maybe combine together different losses. If I'm playing probabilities for this kind of a race of dog and this kind of race of dog that are two different, maybe we could engineering some kind of special distillation loss that could maybe group these two kind of dogs together and to improve the distillation loss. So yes, it could be improved, but as we did this loss, we tried to have the minimal assumption of what would be the classes in our setting. And we also evaluated our model on ImageNet 1000 with more classes, and it seems that it was able to handle this stress.
That's very clear that the proposed method is also generalizing very well to ImageNet, and that's a very strong conclusion. I was wondering if the pooling choice you have not validated on ImageNet, right?
That's yes. I couldn't do it on ImageNet for computational purpose. So yes, maybe there is better pooling for ImageNet. One thing that I have found, I don't have experiment here, but for example, local pod, which was also based on multi-scale, it's actually bringing very few value for CIFAR, as the images are quite small. And for example, this local pod work way better on ImageNet or even Pascal Vogue or Cityscape, but not on this dataset. So definitely there could be some losses that I've missed because I couldn't evaluate it on the bigger datasets.
And to make the link between part of your answer to this question and the future work you mentioned, you're saying that one of the clear next steps would be to start with even stronger starting points. It's universal knowledge. How does that maybe impact the regularization that you want to do at the interpretation level if you really start with these very strong models?
So by itself, I think, first of all, without any using bell and whistle, by simply having a better, bigger pre-training, people have found that it's actually reduced forgetting significantly. So simply have better features that are more task agnostic, simply it will forget less, and it will be, I think, very well paired with losses like POD, which are based on the features and work better if the features are well defined. So I think it should only improve together. Is that was the question?
Into something that I'm for this chapter, there's something you describe in the manuscript that is not in the presentation, that I'd like to just touch a little bit on this. You have introduced this task of pre-trained continual learning, where you assume that you want to classify categories you've never seen.
Mm-hmm.
And for that, you assume that you know the number of categories you will see in the future, and their precise attributes.
Yes.
And if I'm not mistaken, one of the motivations for this particular framework was the industrial application side of the work.
Yes.
So I was curious to know more about the framework where this can apply and how common it is to not know the classes but know their attributes beforehand, and like, yeah, because it also means that your attributes, you cannot continue learning, right? They are fixed once and for all.
Yes.
So that side of thing has a
Yes, so that's a good question. So yeah, in this setting, which has maybe less application than the other settings, it was actually an intuition from my side at Loretech. We haven't put it in production yet, but our intuition was that we have a lot of different closing to learn. I know it's a kind of a shirt, it's a pant, and etc. But for each kind of a closing, we also have a lot of attributes. Attributes that were either checked by a human, but also attributes by a lot of different models that will determine all the attributes of a shirt, all the attributes of a dress, and etc. So we have this kind of information of attributes. So that's one part, we have these attributes. And the other part, we also have knowledge about classes that we haven't yet learned, but that we should learn in the future. For example, if Louis Vuitton asks me to learn all the kind of shoes that they exist, we know we have access to this because it's public information. What kind of shoes, you can just have to go to the website and we'll see this kind of shoes. But sometimes we don't have it yet learned because we don't have yet the pictures. We don't have yet pulled on internet enough picture of this kind of shoes of Louis Vuitton. So we don't have this yet, this class, but we have this information that this class will exist and probably will be incorporated in the future in our database.
Yes. So you may know the class exists, but not have information.
Yes, because actually gathering a lot of images to be efficient is quite costly, both in time and money.
If we can move to the next chapter about
Yep.
continual segmentation.
Yeah.
First, a quick technical question to really understand the extent of this long-range special statistics that you mentioned that, that need to be modeled by the proposal. So, how many scales are you using? Because in the figure here you have two, and
yeah, I only put two scale here. So one and 1.5. At the end, I think I used 1.5, and 1.25, which was bringing the best performance. Using more scale always improved, but it was always a slight improvement. I found that using the smaller scales actually bring the most gain. And simply, so it was, I think, like maybe 80% of the gain was coming from 1/4, maybe then 15 from 1/2, and the rest from scale 1. So simply, the smaller scale are more important, but all the scale contributes together to a global gain.
so basically, in all the experiments you have space, and if
Yes.
you push the number of scales to the limit, it would get similar to something like the pixel.
Exactly. Yes, exactly. The ultimate stuff is actually by doing pixel per pixel, and it will be equivalent to using pod pixel. So I didn't try this pushing to the limit. I think I tried up to 1/8.
It should degrade it, like the classification. Do you think the conclusion will be different?
I think it probably will degrade, evidently, because at the end, as you can say, if we go to the limit, it's 1 pixel per 1 pixel, so it's actually pod pixel. And because we have as much pixel as losses, so they will have much more importance than 1/4 or 1. So at the end, this won't matter anymore, and we have almost a pod pixel loss. So it's kind of an parameter that we have to choose, but it's quite reasonable to use a 3 or 4 scale, which is quite comparable to the literature, from, for example, Lazelnik.
Yeah, okay, now I have maybe more of an open question on the setting of the experiments you run. And I know this is the standard way to evaluate continual semantic simulation. So there's more question about like the kind of evaluation benchmark the community is using. But, you mentioned in this chapter the issue of the background check, right? Yeah. And so first you mentioned that background check accelerates catastrophic forgetting.
Yes.
And I think that's an interesting observation. But do you want to elaborate on what exactly you mean by accelerated forgetting?
Yes. So in our setting, if we're doing image classification, I would have learned the class car with only car in the image, then the class person, then the class bicycle. Every time, only one label in the image. So there will be a forgetting, as it's quite a known fact. But here it's even worse because, for example, on the second step, I'm going to learn the class person. So I'm going to forget car. But even worse, I'm going to see the pixel and the features of the class car that are there present, but they are not labeled anymore. They are labeled as background, which is another class. So I'm saying my model, this pixel, these features are actually belonging to another class. So I'm shifting the meaning of this feature. And by shifting, I mean, it's simply increasing the forgetting.
So by accelerating, you mean like you, like done without care, you add wrong labels to it.
Can you repeat, please?
It means that you're adding wrong annotations.
Yes.
You don't do it in the
It's exactly a wrong annotation.
Yeah, and I think that's quite an interesting observation. And well, you propose this method that like fixes this with a pseudo label and shows how continual segmentation is challenging. But here you still have this very specific assumption that your classes are coming by batches. They are not necessarily a reason why you choose the order of these classes. They come by kind of random batches. You assume that in many cases you've seen them as part of your background. Okay, sometimes you never see them before and you're not enough and you need to do rehearsal, but still you assume that you've seen them until now very often and you ignore them simply. And I was wondering to which extent you couldn't have something slightly more complex when you started deciding to annotate new categories. For example, assuming that you have a car class and you start being interested in the truck class, of course it's going to be it's going to change the way you see the background, but maybe it's going to also redefine some of the foreground classes. Maybe redefine the boundaries between the categories. And at the same time, if you are certainly interested in things that can be parts of other categories, you start having something that is a bit more complex, and you even have something that you could call a background shift, a foreground shift to take your background shift terminology. So I guess I was wondering if you think this is something that would be realistic, and if some of what you developed could be also.
It actually already exists. There is a setting, for example, where it's learning for the class animal. Then the class animal is split in multiple classes, including bear. Then the class bear is split into polar bear and black bear, for example. So it does exist, this setting. It's I think this setting and this setting both have in common that is a conceptual shift. So meaning that the meaning of a label will shift during time. So this setting could have a lot of sense, actually. I think, for example, we could learn a class car and then split it into multiple race car and then family car and this kind of stuff. So it could be applied. And I think we could imagine maybe something similar with some kind of pseudo-labeling. But here in this case, the pseudo-labeling will be quite different, as previously it was the old model that was pseudo-labeling the new classes, because it was trying to cover. Here, if my new model is learning a split of the classes, it will be him, the new one, to have to do its own pseudo-labeling, maybe in some kind of a self-supervised way, to self-supervise to split the two classes from the old images into two.
Do you think splitting is something that can happen organically in a self-supervised manner? Or do you think we start needing some...
It's kind of different, because if we have access to all the new data with the two classes, it will happen naturally. But if we, for example, have access maybe even in the background of we review all images that will only have the class car, there we will need to do some kind of backward pseudo-labeling. Yes, we can hope it happen organically. But then again, when we go to the literature of fine-grained classification, where is it easy or not to really have the fine distinction between two closed classes?
And I guess this is more of an open question, but assuming that you have, like resource is not an issue, if you have right now to rebuild a continual segmentation benchmark, are there things that you would pay attention to, or like what would be your perfect?
Simulation without any storage limit?
So if you wanted to redefine the benchmark, and you can get all the annotations you want, how would you change the current benchmarks?
Okay, so one obvious flaw in the benchmark is that when we do the split of the image, sometimes we can see the same image on the step 1, step 2, and step 3, while only having the new label, which actually doesn't really make sense. And one other thing that is actually very important, and we don't care about it too much, we don't see it that much in Pascal Vogue, but we see it in Cityscape, for example, is actually the class ordering is very important. If I am an autonomous driving company, I will label first the very basic stuff like a road and the sky, which will be the same in every country. Then, for example, I'm learning to classify Vespa in Italy, and then I'm going to India and classifying tuk-tuk, and etc. So a special new learning class. But actually, I found that in Cityscape, the class ordering is actually changing a lot the results. If I'm starting to learn by first the big stuff class like car, building, road, or if I'm learning the small classes like a pole, for example, performance change dramatically. So I think we will need to have a new setting that use realistic images, as Pascal Vogue is not always very realistic, to be honest. And we need to incorporate and to understand why this class ordering changed that much the performance. As in reality, we don't have the luxury of choosing this ordering. So I think that will be one aspect. And then we can also expand to other aspects, as Chamelia has expanded, for example, by using weaker annotation, like only a dot annotation.
And yeah, one quick question. My last question will be a quick question for the last chapter. So this detox method.
Yes.
Well, it's very nice how the transform architecture gets expanded in a very manually efficient way. So I guess I will ask a question about one of the improvements that you proposed for that method, and in particular, the detox plus.
Yes.
Is using a mix-up data annotation where the images are combined, and interestingly, this seems to really help mitigating forgetting.
Yes.
And I find that an easy thing to apply to the method that has direct results in experiments. So, like, is that something that could work also in other flavors of the approach or the baselines? Could you get such a resilience to forgetting?
So yes. So first of all, I was very surprised to see that mix-up was that efficient, as it's barely improved the performance of the joint model, but greatly improved the performance of the continual model. It did improve other models, so I tried on a ResNet-based model. It did improve it by, I think, a slightly less amount, probably because Transformer gained from mix-up for two reasons. First of all, for continual reason that I've explained on my paper, and also because Transformer actually hard to train, and they, as it has been shown, for example, in the DAT paper, they need a lot of regularization. But they did improve also ResNet, and I think that mix-up has almost no overhead, but only gain for continual. They should be maybe incorporated in the standard continual training for future works.
That's interesting. Also, for now, I have many more questions. Very interesting work.
Okay, thank you very much. So we shall continue with the second review.
Thank you. We'll start to say also that I really enjoyed reading the manuscript. It was quite clear. I was in particular impressed by the various number of contributions you had. You touched many of the different techniques that exist in continual learning. So it was nice to see all this direction that you studied. And your presentation was very, very clear, very nicely organized, with all the diagrams and the illustration to link things together to show clearly where we are. So that was very nice to talk. So I had many of my questions that Tian already touched upon, so I will come back to a few subjects.
Yes.
Maybe the first one is about, so you mentioned it in your conclusion also, the idea of having a universal feature, universal representation. And in the evaluation of PodNet, you can see that because you train on 50 classes first, and then make incremental learning of the next classes. And what is your point of view on that, in fact? Because if you imagine having universal features at some point, would it still be relevant to regularize and work this feature with an approach like PodNet? You say that in your answer to Jan that it should work well together. But if you have universal feature, is it really interesting to specialize them on the first classes? Isn't there a risk that for the next classes it's detrimental? It's a very general question, but
if
you have very nice universal feature,
yeah.
Is it still relevant to do some regularization for continual learning?
Actually, so it's more hypothetical, as I haven't yet was able to train a model on very diverse datasets. I think it will be still relevant, but simply we will shift the goalpost to higher complex task. For example, we can imagine that here I'm simply learning new classes, but what would be a true content learning model, maybe AGI stuff, it will be a universal pre-training, and then I will maybe learn some kind of depth estimation, then I'm learning, for example, reinforcement learning, then I'm going to learn other stuff. I think we will need to expand and move the goalpost to more complex tasks where the shift is even higher and where I think the constraint will be needed. So maybe evidently if the universal go to infinite, it already has seen everything, no constraints are needed anymore. But I think there is so much task that we can imagine that we need to have some kind of AGI, that at some point we will still need some kind of constraint.
I have no question about the numbers that you report and how you reach them, in particular how you tune the hyperparameters.
Yes.
I've been in a PhD defense recently where the student was showing that if you restrict the data you use for hyperparameter tuning, it has a lot of effect on the end performance. So how do you tune your hyperparameter? Do you try to optimize the final performance in the hyperparameters? Do you tune the hyperparameters on a restricting set of the classes?
Good. So first of all, what I want to maximize. So of course, there is 3 metrics usually I'm looking at. The final accuracy on all CNE classes, the average of all accuracies after each steps, and also the forgetting, defined by Chaudhry et al. In 2017. So both all 3 metrics are important. And usually what I do, I usually have the same metrics for Cypher and ImageNet because I cannot run a lot of experiments on ImageNet. And on Cypher, usually I'm trying to take the hardest setting I have. For example, for PodNet, it was 15.1. I'm running 15 classes and 1.1.1 because it was the hardest one. And usually in this setting, the parameter transfer best to other settings that are easier. What I do, I usually split the train into a train val, and then I'm evaluating this way. Of course, it's not perfect, as for example, Yaringal said 3 years ago, that in true control learning, actually, we should not be able to see and to tune on all future classes, as it's not perfect. So we should try to restrict on a subset of the classes, and then do the tuning on the validation of the subset of the classes. So some kind of, like in zero shot, Eldaoud said, for example, of the classes. So I try to do some experiment on this. So the parameters were a bit different, but still usually close, but I still usually need to have a lot of classes because a lot of people in total learning are trying to evaluate on 3 or 4 tasks. But when I'm evaluating, for example, in 50 tasks, the parameters are usually quite different. And the problem is I have a Eldaoud set. I don't have enough classes to evaluate this very challenging setting. So what I will need is some kind of ImageNet-like level with 1,000 classes, but smaller, or maybe should I have more GPUs?
And do you have an idea of the order of the performance difference that you get if you tune, for example, the hyperparameters of the first 50 classes compared to tuning on the 100 classes?
It will depend. I think on Ditox I will have a similar performance, while similar hyperparameter as it was quite stable. But on PodNet, I think it worked quite worst, as I said before. And there is, I think, I don't know if I put something about this. Yeah, you can see here, for example, if the initial task size of a PodNet is 50, so half the classes, performance are great compared to state of the art. If the task size is way smaller, it's still above the state of the art, but by only, for example, 1 or 2 points, so much lower. So in this case, the hyperparameters chosen are usually quite different, and the gain will transfer less to other settings. So I really try to tackle first the hardest setting and then transfer to other settings.
Okay, thank you. So still in PodNet, you discussed a lot and you made a slide on that about the compromise between stability and plasticity.
Yes.
And I would like to link that to a comment you make at the end of maybe sometime we would like to forget something.
Mm-hmm.
So your discussion here about the balance in rigidity and plasticity is linked to the fact that your model has good properties for that. But is it possible to control this this trade-off between stability and plasticity, having some things that would like could choose the right level for a new set of tasks or a new task?
So I can explain in multiple ways. So my loss pod has by itself some kind of trade-off, but it's fixed by the definition of the loss. We can still tune it by simply tuning the lambda, because I still need a lambda. So you can tune more or less the relative versus plasticity, but it would do it class agnostic wise. If we want to have tuning different per class, then we want to understand what kind of thing we want to forget or not, and maybe it's harder. Because when I was saying, for example, we don't want to forget, something that is very important is sometimes we want to forget some kind of spurious features. Spurious features could be features with a bias that could help us to learn these classes, but then this bias will actually hinder the learning of new classes. And it's actually quite, I think even impossible to say the spurious feature or biases exist without seeing other images, other classes. So I think it's maybe an impossible task without having access to the future.
Okay, thank you. A small question on the dataset. So you did not present it today on Ghost using
Yes.
the zero-shot setup. So I'm not really familiar with that. But you don't mention it a lot in the end of your PhD. Do you have ideas of extension of this? Or do you feel it as a nice future in front of you, or is it interesting experiment? And,
so actually, I didn't make any slide about it. So I think Ghost was actually a very interesting idea. I think maybe I'm biased, but it's quite beautiful to understand, to have an intuition of what could be the future classes and to make some kind of special exclusion zone in the feature space for it. So the idea is quite nice and it has some results. I don't try to push it further as actually zero shot is super hard to make it work in practice, engineering-wise. You have to tune a lot of different parameters, and it's actually quite brutal usually. Even a set of different methods, if you tune something, maybe you can increase by 20% the performance of the seen classes, but not the unseen classes, etc. So it's very hard to tune, and I choose to switch to settings that were more stable. And I think maybe the future of no zero shot is maybe like very large model, maybe like clip-wise, which I don't really have access to.
Okay. And so for the last contribution about around transformers,
Yes.
so I'm not 100% familiar with this architecture. I was wondering in your decoder, so you are just using one layer.
Yes.
Would it make sense to add more layers?
That's a good question. I wonder the same. And actually, using two layers slightly improve the performance, while obviously increasing the term of parameters by like maybe 2 or 3 million. And adding 3 didn't bring any performance. So it was quite interesting for us because in the literature of conditioning, there is other conditioner, like for example, a film, which was a conditioner introduced for V2A, and actually try to condition the whole network at multiple levels. Otherwise, it doesn't work. But the conditioning is very basic. It's simply a linear interpolation or linear transformation. So it's very basic, and they need to do it multiple times, while our conditioning is apparently sufficiently complex that only one is enough in order to condition the features.
And for the first part, so you use encoder. I think you made transformer for
yes.
encoder. I think you made some experiments with conditional networks.
Yes.
If I remember correctly. What do you think of these alternatives? For example, we could imagine having a ResNet encoder and using pod for regularizing the evolution. Would it make sense, or is it really two different approaches?
So actually, I tried pod on a transformer-based architecture for the encoder. It didn't work very well, probably because I was like, there's token. I'm reconstructing the token as a pseudo image and doing pod on it, and I'm splitting the token. I think it was quite unnatural. But I tried also pod here on the ResNet backbone. So ResNet backbone, as I shown in the performance, were actually quite similar to transformer backbone, while slightly under, but they were still working in our unified framework. And when I tried, for example, here, Data's ResNet with pod or with local pod, both of them did improve the performance. Very few in average, but in the last accuracy, doing like a 2-point accuracy gain, so which is always beneficial. One thing that I want to say is that I think that pod and Data's are quite orthogonal as they try to aim the different kind of thing. And maybe it's less important for Data's as for PodNet, I have forgetting very important on the feature-based level, while in Dictox, maybe this is forgetting, so it's an assumption, that it will be less important as my conditioner during the fine-tuning phase can quickly be retuned, the decoder, in order to adapt quickly the feature with that shift. And also the local pod here is less good than pod because simply I'm evaluating on Cypher, which is smaller, and I think on an image of 32 by 32, having multi-scale doesn't really make sense.
Okay, so just one last question on the transformer. One of the interests or feature of transformers that it's supposed to be somehow interpretable. You have some attention that could give you some information. Do you have an idea if this is true here? For example, if in your task decoder, can you have some insight about what is going on? Having an idea of why it's working well.
Yeah, so on Cypher, we don't even need to try because I couldn't see anything as the image is way too small. On ImageNet, usually it's quite hard to determine as it seems that all task tokens try to focus on the same on the salience object. So it was not very useful. So I think in this case was not useful. But maybe we could expand Dictox maybe by using some kind of similar to the hierarchical perceiver, maybe, is having it's not a one task token, where a task could have maybe multiple dogs, another task could also have multiple dogs. So it doesn't make sense here. So maybe more about some kind of hierarchical where each classes, for example, it could be a token for each dogs, or a token for each cat, and etc. Or maybe a token per class. And here maybe we could maybe more interpret what are the feature learning and what is the attention pattern.
Okay, thank you very much.
Thank you. So let's continue with Tatiana Tomazi.
Tatiana, can you?
Yes. Thank you. Thank you for the presentation. Very nice. I also appreciated a lot the thesis. Well done, well organized, very clear. I just have a couple of questions since most of my doubts have been already answered by previous questions. So let's start from the Dictox.
Yes.
Okay. So so my question there is to have some. I would like to have some clarification about what happens at test time, because it's not fully clear to me how the tokens are used at test time. If I have to know the new image which is coming in, to which task it belongs, or if I mean it's not important to know it.
Yes. Actually there is two ways in content learning to predict. It's a single-head setting or the multi-head setting. In the single-head setting, we don't have access to task ID, and we have to predict among all scene classes, which is actually the most realistic setting for our tech. In the multi-head setting, we have access to task ID. So we know which subset of the classes are useful, and maybe we can also select only, for example, we could select only a branch of the decoder. In our setting, we only evaluated on single-head setting, meaning that I'm doing, for example, if I've learned 3 tasks, I'm going to do 1 forward to the encoder, and then 3 forward to the decoder, 1 for each task, theta 1, theta 2, and theta 3. And then I will have 3 sets of logits for each task. I'm concatenating all the logits together, and during training, it's a sigmoid plus binary transformation, and at test time, it's simply doing the argmax for the biggest logits. And so I don't need any task information at test time.
Okay, I see. Okay. Then regarding instead let's say chapter 3, so the first method, well actually it's related to ghost, so the second part of the third chapter. I was wondering in terms of applications, I mean, you mentioned that you might have attributes for let's say shopping things that you want to sell, and it makes sense to have these attributes, but I guess that it might happen that you have fine-grained problems. I mean, not necessarily completely different categories, but categories of the same type with attributes that differentiate from subclass to, I mean, several subclasses in the same category. So I was wondering if this kind of setting is challenging, how more challenging it is with respect to the separate categories that you considered, and if it makes sense to still use it there.
So if I understood right, your question is to expand Ghost to setting with even more fine-grained animal classes, right?
Mm-hmm. Yes. Yes. I mean, if your problem is a fine-grained classification, so your attributes are actually differentiating among multiple subcategories of the same big class, let's say.
So I kind of already does that in a way as, for example, one of the dataset, AW2, is a dataset with animals, and several animals actually are quite similar together. So the attributes are enough in order to discriminate. For example, there is different kind of bird, and one attribute could be a bird with a blue tail or brown tail, for example. So it's a very fine-grained differentiation that could be incorporated in the attributes. But then I could also expand my datasets, as I said in the introduction of the paper, to other datasets, such as, for example, iNaturalist, a set made of animals and plants, which is extremely fine-grained. And in setting, we also have attributes. So I think Ghost could be applied on this setting. Then again, if the setting is too fine-grained, we could also wonder if the exclusion zone in the feature space will be also fine-grained enough or not. Does that answer your question?
Yeah. I mean, I was just want to. So in practice, you did already some experiments there, and it still makes sense. It still will still work. Okay. So another curiosity still on this same method. So there are some part of the thesis that were not fully clear to me, because you say that the generator is actually producing features, while there is another point of the thesis where it says that the output of the generator then goes into the feature extractor. So I'm not 100% sure if the generator in that particular case is producing images or is producing features. Just a clarification on the technique.
No, so it must have been a mistake by myself, because the generator is actually trying to mimic exactly the feature that will be extracted after the global average pooling of the ResNet.
Okay. Okay, so I mean, yeah, I mean, I had just a few questions since most of my doubts have been already answered. So thank you very much, Arthur.
Continue with Cathy.
Thank you, Mr. President Kevin. And thank you, Arthur, for the wonderful presentation that you've made. It was really very clear, and you connected all the parts of the thesis in a very, very clear way. So, okay, coming as a fourth person to ask questions is always tricky, because many of the questions have already been taken. But I have still some which hopefully are interesting. So the first one is actually on this on the third chapter of your coordinate.
Yes.
So here, I think it was also brought up in the previous questions that you do require a minimum number of classes on which this model has been trained. And you said 50 was the one that was. Sorry?
Component.
Yes.
Yes.
And then you added whatever number
yes.
of classes after. So here I want to check with you about the how realistic this setting is, because the performance does go down when you have fewer number of classes that you start with. But there could be applications where perhaps you don't get this kickoff at the beginning with all these classes given to you. So in those cases, how would you recommend to adapt the method?
So I have two orthogonal solutions. First of all, usually I think no one in the industry usually base their model on a randomly initialized model. We could at least use a pre-trained model on ImageNet, for example, that could still provide features that would be, I think, enough to complement the fact that the first task is too small. So first of all, yes, a pre-training. And other axis also, people have shown that, yes, as soon as we reduce the initial task size, the forgetting is higher, but it could be also reduced if the first task is shown in a self-supervised manner. For example, you take like a Dino Swab, for example, or Biol, very high-end self-supervised method, and they can learn efficiently class-agnostic features, despite the fact that that set is quite small, and that can almost alleviate the fact of the small task size.
So that's very true. But as a follow-up, so here there could be issues with, for example, some of these models could be using some of the classes that you will only see in the future, right? Even though you don't have the labels, but all the data is already available. So do you think that poses problems?
So this is a problem of data leakage in academic setting, but in the industry setting, I think we won't care about it because we just have better performance. So yeah, in the academic setting, it could be a problem. It's actually why it's quite maybe I would say taboo in the content learning community to try to have some kind of pre-training, as we don't even know if the pre-training can kind of leak information in the future. So in this setting, we will maybe need to evaluate on a new kind of data set. For example, we could do pre-training on ImageNet and then do a control setting on, for example, medical data on different kind of tumor, for example, which are very different and nothing alike with what we would see in ImageNet, but still the ImageNet pre-training will give, maybe at the first level, will at least give some kind of class agnostic features that could help the content learning on the medical data sets. So maybe we will need for academic to shift the data sets to other settings.
Great, thanks. So let's have a sort of a detailed level question. So in many of the results that you show in particularly this chapter, you showed the variances, which is I think great, how the performance varies. So I'm not sure if I got the detail for all of them, but can you please say how this was done?
The variance usually I'm taking the same seed, usually a seed of 1, remember, and I'm trying a multiple class ordering, as I've shown, for example, I think in the plot paper, that the class ordering will change the performance of other models. So usually I'm trying different class ordering. If I can try all class possible ordering, like on Pascal Voc, I tried all, but also sometimes tried 3 or 4 or 10 times different class ordering taken randomly. Usually the literature will all take the same random class order and we evaluate on this, and this is the variance.
Yes, but I suppose this variance will depend on, I think you mentioned earlier, like it depends on the data set. For some data sets, change the class order was significant in terms of changing the performance, but for others it was not. So I'm wondering if you should also look at changing the seed itself to see within your model how much randomness is generated, or have you looked at the seed? Or
yes, so in most experiments I do with the fixed seed, as it's easier to handle the different variation. But usually I try different seeds also, just to see. Usually the performance doesn't change that much, I found, at least not in Ditox and PodNet. I don't remember for Plop, but I don't think performance changed very much. And I think for Plop they change even less because the backbone is pre-trained on ImageNet.
Okay, thank you. So one other question in the same work of PodNet. So you showed, which is again was very great, is the different variants of PodNet. One I think you call PodNet CNN, there was the PodNet NME.
Yes.
So here I was to contrast between these two in particular. There seems to be some sort of difference in how they perform. Like I think I have it actually here in the thesis. It was on page 40 from the table, where the performance of PodNet CNN seems to be good right across, but I think it was in one more where PodNet NME isn't always, for example, the best.
Yes.
There was one other method I think for you used 200 examples in the memory. It was significantly worse than one of the previous. So I'm wondering why this anomaly happened. Do you see any reason why?
So just to recap, PodNet CNN is based on doing, so both are trained the same way, but at this time, PodNet CNN I'm doing argmax among all the logits, while for PodNet NME, I'm taking an exemplar feature for each class and doing a KNN among this feature space. So indeed, on CIFAR, NME is better. On ImageNet, CNN is better. And if I have a very small memory, NME is better than CNN. But also, if the memory is very big, CNN is better. I think it's kind of linked to some kind of maybe, first of all, some kind of rigidity as the feature space as forgetting because of the feature extraction. But maybe it's also less forgetting than the CNN, as there is a forgetting that could also happen in the classifier. And there is also a method in order to recalibrate, for example, the classifier to avoid the forgetting of it. But I didn't try those. So maybe the NME worked very well, very few memory, because it doesn't suffer from this shift and forgetting that could also happen in classifier, as there is no classifier used at this time. And also I found that on ImageNet, usually CNN worked better. So I'm not entirely sure why. I think it's probably linked to what we could see in the retrieval literature, where in retrieval literature, usually we go in big data sets and we're going to extract the feature and do a KNN on this, so kind of like NME. And actually, they need some kind of big pre-training, maybe even better to have representative features. But here in our case, we don't have a big pre-training. We don't pre-train on whole ImageNet as they did usually. And maybe the features are way bigger. Therefore, the space to search is even exponentially bigger for the enemy. And in this setting, it struggles simply because maybe of a curse of dimensionality, where the CNN doesn't have this problem for ImageNet. But that's only a ad hoc hypothesis.
Okay, thanks. So I'm wondering from this, I guess coordinate CNN is more like maybe the end-to-end kind of model. Maybe the coordinate enemy, you can call it as not end-to-end.
Definitely, yes.
So from this, can we make any extensions for, you think, it's not quite the end of the end-to-end, because it still works better in some cases. So I was wondering if you can say, like, okay, in which circumstances maybe would you say that when you have less examples and less examples that you can store in memory, it's better to not go for an end-to-end approach? Can we say that conclusion, or?
We could imagine some heuristic. I think it's always hard and brittle as a way. So maybe if we want to expand in this direction, what we could do is maybe some kind of ensembling, where maybe we could ensemble the prediction of both the CNN, so the probability of the CNN, and maybe combining with some kind of normalized distance of the enemy, and combine both by voting or by averaging each of different predictions, and maybe it could combine both of the best of the both world. And we could also have some kind of notion of uncertainty based on probabilities, or notion of uncertainty based simply of some kind of inter-class witness of the features for the enemy, to understand which one is uncertain at which moment, and to maybe give more importance to one of them during the voting.
Okay.
That makes sense.
Yeah, thanks. Okay, so I'd like to move on to the next main contribution that you presented, which is the work of plot.
Mm-hmm.
So here again, here you present again two different variants, plot, and I think all the other one is plot long.
Yes.
And again, here, in some cases, the first one seemed to work better than the other.
Yes.
And the opposite in certain cases. So I was wondering if we can get an intuition for why this happens. I mean, it's perfectly normal for two different models to be able to, but I would like to know if you have an intuition for why this happens.
It's not like I think the plot long work better than the plot. It's more like the plot long work less worse than the plot on other settings. I think it's more in this direction. So it's based more on the metric learning literature. It's quite close to some situation that I did in code actually, with some kind of constraint classifier and this kind of stuff. Constraint classifier, I feel harder to learn than a classic classifier. Therefore, on easy setting, we are better off with a classifier. But on very hard setting, for example, 10-1, that I did an experiment with 10 classes, then we learn 1 classes by 1 until we have learned 20 classes, so 11 tasks. So this is very hard, and this setting simply cosine we forget less. One of the reasons is because of the normalized magnitude. But also all the frozen BRNN and this kind of stuff that can help. I think it's simply because it's so rigid. All the model of plot long is so rigid compared to plot that simply forget less. But also it's I think probably a worse model if we have access to a lot of data. So it's very specialized to some kind of maybe extreme and academic settings.
Great, thank you. So the other question I have on the same topic is, so basically you talked about some of the limitations, and I think the issues that you have potentially with the pseudo labeling will be presented in the table in the slides. I don't have any more. But so that definitely is one potential issue. But do you see other limitations of this work of using pseudo labels? Are there other issues?
That the pair model is imperfect, and the pseudo label is quite imperfect. And I found that on some situation it was hallucinating too much of pseudo label, which was a problem. There is also a problem if there is some kind of covariate shift where the input pixel will shift. For example, I take the example, I'm learning classes in Europe, and then I'm going to India, for example, or to Italy, and it's a very different environment. Maybe the luminosity is not the same when I'm learning the new class, and simply it will make covariate shift where the pixels are very different, and the pseudo label will simply make anything bad, and even the sorting metric doesn't make sense anymore because it's a new data set and it will struggle. So I think more data set shift, which actually is an important problem in autonomous driving for segmentation, where our model will struggle in different environments. That I think will be my idea.
So this is also great for semantic segmentation, but I'm wondering, so the next type of segmentation that would be interesting to consider is instance segmentation.
Yes.
Is that a case you've looked at?
I'm actually co-working with Fabio Ciammelli, who is present in this room, and we are working on this kind of extension, yes.
So would you think this model that you presented here will not extend directly, but would you recommend using this model as a starting point, or do we have to look at the problem differently?
We are considering about using the plop listation, which is useful, and pseudo-billing, and also transformer-based like Datox. But anyway, it's, I think, very important to use some kind of pseudo-billing. I think I didn't took too much literature for the recent control segmentation, but in every setting, it seems that they use some form or not of pseudo-billing, as it's, I think, very well, maybe essential to this setting, and we will probably need to use that.
Okay, so I have maybe just a couple more questions. The next one is on the last part of your thesis.
Yes.
So here, this attention modeling is great. People are using it all over the place. But here, I was wondering, especially in this case where your attention models are evolving over time as you see more and more tasks.
Yeah.
It's always tricky, but you see a way of visualizing these, at least some of these attention modules that are being learned. Is there a way to understand what is happening?
Yeah, I think it's probably the same answer as I did for David. Attention patterns are quite messy for Cypher. We cannot see anything. And on ImageNet, I didn't see any clear pattern between, for example, the pattern extracted by theta1 and theta2. I think that's for two reasons. One reason is that visually, at the human level, maybe not at the feature level, at the human level, they seem to extract some kind of saliency, so based on what is the more salient object and the features. So I cannot say whether it makes a difference. And also, when evaluating on ImageNet, the problem is ImageNet with 1,000 classes, but I think there is 133 classes of dog. So the thing is, probably the class dog is in the first task, on the second task, and the third task. So there's dog in every task. And at this point, maybe each will learn the same kind of pattern of attention because of that. So we will need maybe to split, to put all dogs in one task and put all cats in another task. And then maybe it will be maybe clearer to see what the pattern is correctly learning. Because right now, it's learning something efficient for content learning, but it's more at the feature level, not very interpretable for the human.
Thank you. So this may be sort of a follow-up question to what Diane was suggesting earlier around the data sets. So yes, clearly, they're using existing data sets and people have been adapting them to continual learning settings. But I think it's really time to just start from scratch and create a new, real continual learning data set? Or
I think that's something that a lot of people want to do. I think every year there's someone who releases a new content data set that will change everything. It has yet to happen. So I think, yes, that's something that should be very important. But the question is, we have to balance multiple trade-offs. It has to be big enough in order to be representative, but not too big, because we want that still PhD students can run on it. What do we want? Do we want some kind of class incremental, domain incremental, concept shift? So there's multiple kind of shift we want. Maybe, like Dan said, do we want also to have at some point that some classes split into two different classes, or maybe even the opposite, that some classes get merged back? So I think there's a lot of different settings, even if you do classification, segmentation, object detection. So I think we cannot have one single data set. And we simply have, as we have in content learning right now, the number of papers explode. At first, it was only five papers at CVPR, now it's 45. But each is evaluating on very different kind of continual flavor. And I don't think we can find one unified setting.
It's not a good one. So maybe I'd like to end with one question. So you did like several contributions in your thesis, but I had to put a gun to your head and say, okay, choose the one that you like the most, or you think is the highlight of your PhD. Which one do you think?
The one I prefer.
I think yes. I think it probably will be pod. It was maybe the first model I defined, but it's actually quite versatile. It's been applied in different settings. People have also applied the loss in model compression, for example. So nothing like content learning work quite well. And the intuition of doing this is actually very efficient. And recently, in the same time as my publication, other papers are published in different settings, not continual setting, losses that are quite similar to pod, and they all found a very interest of doing this kind of width and height axis. I think this is the one that has the most merit.
Right.
But maybe Mathieu will say otherwise.
Yes.
Thank you again.
Thank you.
Okay, thank you very much. So we'll continue with Thomas Robert, which is the supervisor, I guess.
Thomas?
Do you hear me?
Yes.
Okay. So I don't think my role is to ask any questions since I worked with Arthur doing his PhD. But I would like to thank him for this very clear presentation and mostly congratulate him on his very successful PhD. As you've seen, he's published many articles in great conferences. It was really a pleasure to have Arthur working at Uritech with us. He's extremely talented and also very passionate about deep learning, and I'm always impressed by how broad his knowledge of deep learning state of the art is. His knowledge is going very far from his area of expertise of his PhD. That's always very impressive. So I think he will be a great researcher, and I wish him the best for his next position.
Thank you, Thomas.
Thank you. So let's continue with Mathieu.
Okay. Thank you, Kevin. First, I would like to congratulate you for your very nice presentation today and to thank all the jury for coming and for the reviewer for their work before the defense. And for all the questions, it was really a pleasure to have this discussion. Of course, I don't have any question for you. Arthur, I just want to mention a few things on your work. First, I'm really impressed by the quantity and the quality of the contribution that you give for the community on this subject of, let's say, incremental continual learning for computer vision, of course. Yes, I'm very impressed because you are very, easy to work with as well, classification task as segmentation. You were able to switch from one to the other and reversely to come back with different kind of architecture. So no problem for you to tackle and to use and to work with transformers that are very new into the domain and to be able to have a contribution on top of the classical calling transformer architecture that you are going to present next week in CVPR. So architecture, no problem. Idea and task and handling all these things very efficiently, no problem. And so you are very, very efficient for implementing and so fast to get so dark. Whatever the type of architecture you are considering. So it's really, it's really very clever for these things. And I think you published a lot that has been mentioned. Differently, I have to say that perhaps only the work about the prescient and the ghost have been more difficult to be published, and finally we switched to a workshop and CVPR workshop. It was a good one because with the Conference Act and so on. So, but it was less easy perhaps to, and I think it makes sense with the type of question. It was not easy because it's necessarily another kind of data set and another way to define the task and the increment that we can have and typically you had some question because it's not a usual framework and use case that we can have. But it was also I think certainly Thomas will be agree with me that it's one of the certainly the kind of context that we can have at Uritech development because typically we can have some was really some of the use case that we identified that makes sense for Uritech or some kind of company, fishing company working on fishing, that where you know that you are going to have the 100 classes, you know the test classes, but of course the images year after year or are not coming all them together, and so you have to deal with this kind of things. So, but okay, not very easy, and I really think that, okay, as Kartik mentioned, I mean, certainly, I mean, like the most interesting context for continual learning has to be defined now. So perhaps you are going to contribute to that in your next job. Okay. I also, so if I have to summarize you in one word, I would say fast. And if it's two words, I would say very fast, because I really think that, and it's of course. So sometimes I say to you, oh, slow down, okay, slow down, and think perhaps you miss something that you didn't see because you go too fast. Okay, so this is really my advice that keep certainly, I mean, makes sense. Okay, still makes sense. Is that okay? Sometimes, yeah, keep good. But of course, this is so. But you are very strong with that. You are very fast to react. You are able to finish your PhD even before 3 years with so many, as we say, publication contribution. You have a lot of citation content, so it's amazing. It's amazing. And certainly to finish, I would say that whatever all these things, you are very, I mean, like, you are very friendly to work with. You are really open-minded. All the time, you really ask me and you listen to my advice to improve yourself and during these 3 years. So that's a very good thing also. And you were very, I mean, like, happy to participate in the life of the team and also for the teaching, and so all these things make that. I'm really, like, really happy to have this time with you during these 3 years, and I'm very happy, of course, that for the following for you in this very nice company. I mean, one of the strongest one at the moment, and so yeah.
Thank you. So I will finish the question session.
Yes.
First of all, I would like to congratulate you for this work and for this presentation. It was very clear. As already mentioned, it was very good job. And it shows through a very strong publication track record. So congratulations. And I'm not an expert in continual learning, so it was a good occasion to dive into this subject. And I think it was a good starting point for that. And so I recommend other people to read this thesis if they want to start with this domain. And I don't have a lot of questions. My first question is about PubMed.
Yes.
I was quite surprised in the adaptation study to see that GradCam strategy 39 has very poor results compared to other polling strategy, and even compared to no strategy.
Yeah, GradCam is actually based on it's kind of similar to code pixel, I say. There is no, so it's only the last level. There is no pooling, and it's kind of code pixel on the last level, but without some kind of ponderation based on the gradient. That's what it's implemented in learning without memorizing. Paper that I think no one is able to reproduce it, and I never make it bigger. And I mean, the loss is quite simple, and there's a lot of implementation on the internet of GradCam for the interpretation, but to implement it in content learning, I was never able to improve the performance of it.
Okay.
So I think maybe the gradient estimation maybe only makes sense when the model is already quite well trained, maybe with a even bigger text size, because usually GradCam they use it maybe on bigger data sets such as ImageNet. Once the model has trained on the whole ImageNet, while in our setting it's maybe on smaller data sets, so that's CIFAR, and the model has only trained for a few tasks. So maybe at this point GradCam is less informative, and therefore it's revert to some kind of pixel model.
But apparently there is the same problem with perceptual style also.
Yes, but this loss was defined more for visual features such as still transfer by Johnson et al. In 2015, and I don't think it makes very sense in our settings.
Okay.
but I did implement it for the sake of completeness.
Okay. Thank you. And I have now a more general question about continual learning. And I'm wondering how you can simultaneously consider new classes and domain drift in your data. To make it clear, for example, if I train a network on images from the US to detect cars, to segment cars, and now I want to detect a bicycle in the Netherlands, how can I address both the fact that I have a new class at the same time that the cars in these new images can be not exactly the same as in the US?
Yes. That's a good question, and I think it's this setting that PodNet, at least the pod loss, will shine compared to other models. There's a lot of distillation loss are based on the class probabilities, but maybe on this case we simply want to focus on the features probabilities. So maybe pod will force that maybe if it forces that the new model has similar feature statistics as the old model, it can reduce this shift. This shift could be also reduced in other ways. I contributed to a paper with Antoine Saporta as a main author, which was published at this workshop this year of CVPR. And what we did in this setting, we also have some domain adaptation, so new car in different kind of cities, for example. And we also could transform the pixel space by simply taking features or statistics of the pixel space of one domain. For example, simply the RGB, but in another space. So I think it was a LSV, I don't know the name of the color space anymore. Then we simply apply a linear interpolation or transformation to shift from one color space to another color space. And it could actually work quite well to cross the gap between a slight covariate shift between, for example, two cities, which has a slightly different luminance.
So you think that in pod, it's implicitly incorporated?
We actually use pod in this workshop paper, and we use both pod for the features, and we did also this shifting of the pixel space based on the color space. And both of them contributed together to improve the performance.
We'll switch some questions. So finally, I would like to ask for communication. At the end of a thesis, if you have just one direction, research direction that you want to continue for a new PhD or for a new PhD student, what do you see this?
I'm biased, but I think content learning is truly important. It started to grow significantly from the last few years. Content learning is important as it's not the end by itself, but it's rather a tool. And at some point, every big model, like all the foundation model, start to have an impressive performance, but they're so big that it's very hard to train a new one. And content learning could remediate that by simply always improving the performance. And a model should not live for a few months when we train it and evaluate it and publish a conference, but it should live for 1 year, 2 years, 10 years. And every time we improve on this model using content learning. So I think it's very important. And it's maybe one of the essential tools for kind of AGI. And where in content learning, I think one of the important field will be maybe the composition of expert, is maybe to understand better what's learned and maybe how to, as a human, to composition together different kind of knowledge to build a deeper and more complex knowledge, which may be also linked to some kind of causality also, in order to understand what does really matter in order to learn something and not to learn spurious feature or biases that will simply induce a forgetting, that simply learn some kind of agnostic and some kind of invariant that could transfer well for content learning. So yes, this knowledge of composition, causality, and invariance, domain generalization, actually are essential for both content learning and maybe the whole field in general.
Thank you very much, and congratulations again for your work.
Thank you.
So, I'm going to
we stay here.
Je viens du tout.